Do you have any questions so far? No. Okay. Yesterday I talked about neutron star. Did it click you what it is? Why I was talking about neutron stars? Degeneracy pressure. So, in the case of an electron gas, you may still sort of you may be inclined to think that it could be that there is this electron repulsion that prevents the electron gas from collapsing at 0 temperature, right? Even though I told you right from the beginning, in fact that's the model, Sommerfeld model, where we ignore the electron repulsion. But the existence of neutron star is a proof of the degeneracy pressure, because in neutrons have no charge, so they cannot repel each other electrostatically, isn't it? So, the existence of neutron star is a proof that in a gas of fermions there is a degeneracy pressure, which we calculated yesterday, right? So, now yesterday I also talked about specific heat, which is one of the most important points of this model, but I did not do it very neatly because of the time shortage that we had. So, today I will repeat some of the things that I said yesterday and probably do it in a little bit more better and efficient way. So, first let me explain to you where is the problem. Why do we want to spend time on specific heat? So, if you go by the classical theory, then the energy of a gas per unit volume, electron gas per unit volume, should be how much? Should be 3/2 kBT is the energy associated with each electron, right? And since there are n electrons per unit volume, little n, so the total energy of the gas at temperature T should be 3/2 n kBT. This is the classical result. Classically, this much should be the energy. Energy not by virtue of repulsion. This is purely translational energy, isn't it? The electrons are moving around because of the temperature T. If the temperature T goes to 0, the classical energy would also vanish. Right? And then if you take the temperature derivative of this, then you should get Cv, and this should come out to be 3/2 n kb. Right? So, that is our classical result. Now, for for the in the metal, you also have the lattice besides the electron gas, right? And lattice you have already studied, and you know that at sufficiently high temperatures, the specific heat of lattice or the lattice specific heat goes as 3 n kb, because there are 6 degrees of freedom, right? So, from here what we so I'll come to that in a minute. So, just to point out that according to this result, the specific heat of an electron gas should be temperature independent, one, and should be 3/2 n kb for all temperatures, right? So, there are two points that emerge from here. One is that it is a constant with respect to temperature, and the second point that emerged is that its value is 3/2 n kb. That is the magnitude. Now, if we combine with the lattice specific heat, so this is for electrons, so I will write EL now, and then similarly I can write CV, specific heat at constant volume, for the lattice, lat, and CV lat at high temperatures is 3 n kb, right. So, that means if you go by this, then for a metal you would say that at sufficiently high temperatures, the total specific heat should be 3 plus 3/2, right, should be 3 plus 3/2, 3 coming from lattice degrees of freedom and 3/2 coming from the electronic degrees of freedom, right. So, the total specific heat going by the classical laws should be 3 plus 3/2 n kb, or 3 plus 3/2 kb per atom. But the experimentalists found that the specific, even for metals, the specific heat at sufficiently high temperatures is just close to 3 n kb, which means this 3½ NkB is not seen experimentally. Okay. So, the reason is that the electronic specific heat even near room temperature is much smaller than what classical theory predicts. In fact, today we are going to show that the specific heat near room temperature of metals is about 1/100th of the classical value, right. So, if you add this to this number we have seen we get experimentally 3 kBT. This is Dulong-Petit law. So, to this number, if we add 1/100th of this number, okay, then it will be a very small change. So, that in experiments you may not be able to clarify. So, so that is what we have to fix. That problem has to be fixed. The specific heat of electrons is very small at low even at room temperature. And second problem is that the specific heat of electrons in a metal is not a constant. It depends on temperature and depends linearly on temperature. Okay. So, these two problems needs to be fixed. So, now you know that this model is not going to answer the thermal properties. The classical model fails miserably when it comes to thermal properties. So, we are led to the Sommerfeld model. Okay. And here I don't need to repeat myself. So, you know that the density of states d of E in this model, it goes as square root of E, right. You agree with that? And you fill up the states, you build the ground state obeying Pauli's exclusion principle and filling up the states of lower energy first, right. So, you fill up the states in order of the energy. So, if you plot this function d of E, then this looks like this. So, if you have this d on the y-axis and energy on the x-axis, then it's a function that looks like this, right. So, that is the density of states, how the states are varying. Now, you also know that your Fermi function, the distribution function, how that varies with energy. So, the distribution function is 1 up to the chemical potential and at 0 temperature, and for metals for all practical temperatures, this is EF. Okay. So, that means if you have to draw the 0 temperature, at 0 temperature, if you draw the product dF. So, on this y axis, if I plot dE Fe, this product. So, then this product is drawn with this orange color. So, it's going to look like this. Sorry, okay, go on this and right up to here, and then okay. Now, at a non-zero temperature, the Fermi function deviates and it does something like this, right. So, this is at T not 0. This is at T equal to 0. So, the corresponding product function would again do something like this. Okay. So, this part depicts the empty states and this part depicts the filled states. The states that were unfilled at 0 temperature have now finite probability of getting filled, right. So, from here, if I ask you what should be this quantity. So the question is, at t equal to 0, how much is this quantity? 0, I am integrating from 0 to infinity, the quantity d e dE. Suppose I am integrating not from 0 to infinity, but 0 to EF. Let me see who will answer this question. That will give me an idea of how much you have understood. What should be this quantity? Total number of? Total energy. It will be total number of quantum states, isn't it? Because dE gives you the number of states in the shell. And when you integrate it from 0 to F, that gives you the total number of states. And total number of states is same as total number of electrons, because each electron takes one state, right? So therefore, this is equal to n, right? Next question. So this is identity number 1. The next question is, how much would this be? Integral 0 to EF E dE dE. What should be this quantity? Sorry? What is your system? The electron gas. So say that the ground state energy of the electron gas, U0, right? And because the density of states, the way it is defined, is the number of states per unit volume. So this will be the ground state energy per unit volume, which means it will be U naught V. Sorry? Sorry?
The first integral,
It
should be n, small n.
Should be small n. You're right. It should be small n. Absolutely correct. Why? Because the way we have defined density of states is per unit volume. Now, at non-zero temperature, how these equations are going to change? So the corresponding equation corresponding to 1. So at a non-zero temperature, the electrons are not restricted to the region from 0 to EF alone. There is a finite probability of finding the electrons in this part above the Fermi energy, because you have increased the temperature, and so what you have done is you have smeared this function. So inside this line, and the width of this line is kBt, you remember, inside this line the function is still intact, because these electrons, the electrons that are occupying the deeper states, they do not have enough energy to come out, but these electrons can, and they explore these states that were previously empty, right? So the corresponding relation in this case would be, instead of integrating from 0 to EF, you have to now integrate from 0 to all the way up to infinity, right? Of course, for very high energies, it will be impractical. The contribution from the integral is very, very small, right? The main contribution will come from this part, then it decays. But ideally, we should write 0 to infinity, because we do not know where exactly the contribution will become negligible. So 0 to infinity, and then you will write again dE dE, and this should give you your total number of electrons back. But this time, oh sorry, is this correct or is this correct? Because you see, dE is this solid, white solid line. This is dE. dE has nothing to do with your electrons. Unless you multiply dE with Fe, you are not talking about the occupancy of these states, right? So now you have to put here the Fermi function also. So this is dE times the Fermi function, the distribution function Fe. That should be equal to n. Right? So what that means is that this orange line, right? That quantity, the area inside that quantity. So essentially what we are doing is this DE is nothing but this area, and this area is equal to your little n, right? We need to multiply it with Fermi function. Of course, at 0 temperature the Fermi function is 1. So therefore the orange line is same as the white one if you cut it off at EF. But now this integral corresponds to the yellow line, sorry, not the orange line. This integral corresponds to the orange curve. This integral corresponds to this. So therefore, this is what it is. And similarly, the corresponding equation for this would be 0 to infinity, and you will have E Fe dE and dE. This quantity will give you the total energy at temperature T. So this quantity will be U V T. Okay. So now these two identities corresponds to 0 temperature, or the orange plot, the area under the orange plot, and these two quantities corresponds to the yellow plot, the non-zero temperature. This is for T non-zero at any finite temperature. Okay, is this clear to you? Do you have any questions so far? Okay. Now if you have understood this, the rest of the things should make sense to you rather fast. And so at any non-zero temperature, at any finite temperature, the total energy of the system U bar, U tilde, V, and this is at a finite temperature T, right? So it is something like this quantity, right? So I should by notation write tilde. I don't want to make the notations very complicated. So it's up to you. You want to put it, you put it. You want to leave it, you can leave it. So this should be equal to the ground state energy UV0 plus the excess energy UVT, right? And if you want the specific heat from these degrees of freedoms, the electronic degrees of freedom, you take the temperature derivative of this. The temperature derivative of this will be 0. So it's essentially this. So CV is essentially del U del T. Okay. I mean, you may put this superscript, you may not put this superscript. By putting it, we are unnecessarily making things very complicated for us. So when there is a 0 here, you know it's 0 temperature property. When there's nothing here, you know that it's a finite temperature property. So let's not put T, otherwise it will become very difficult for us to follow all the subscripts and superscripts. Okay. Now what we can do is we can write this U of V. Now this is just a trick. The what I am going to do is more of a trick. So I can write U of V as this minus this. Right? And I can write for this integral 0 to infinity E same quantity E, Fe, dE, dE. So, to make notation simple, I am going to drop this function of E, because you know that, and from D also the function of D. So, I am just going to write it as E times F times D times dE. That is your first term, and the second term is 0 to EF, and then there, that is E, D and dE. Okay. Now, this integral, this one, this integral you can write. So, I'm writing here. So, you can write 0 to infinity as 0 to EF plus EF to infinity. Right? You can do that, and you can absorb this part of your integral in this part. Okay. So, if I call this as A and this as B, then I have split A into A1 and A2, and I am going to absorb A1 into B. Okay. So, if I do that, then what I am going to get is, what is the best way of writing on this board? So, you will get UV is equal to integral 0 to EF and then E times 1 minus F d dE. That comes from this term. By merging this A1 is merged with the piece A1 is merged with B. So, you get 0 to EF, and then you get F, and there was a minus sign over here. So, all this is included here, plus you get the second part, which is the A2 itself, which is integral EF to infinity EF d dE. EF d dE. Okay. Now, I can be a little tricky and write this term. Is everything okay, or something is not good? Something is not good. There should be a negative sign here, right? You can check that. So here you will get F with a positive sign, and there is a negative sign here. So, if this I pull this negative sign out, then this will be 1 minus F, right. Okay. I can write E as this E as EF or E minus EF. So, this is capital F plus EF, and again divide this integral into two parts. Okay. So, this is not my method. I do not know if this is Sommerfeld's method, but it is very tricky. As you can see, you are just dividing the integrals, but this is how it is, and it is not very long. Do not worry, it will end in another few steps. So, then you will get something like this. So you replace this E by these two terms. So, you will get first term as integral 0 to EF, that will be E minus EF and then 1 minus F d dE. Second integral will come from here, minus EF, EF being a constant, it will come out of the integration sign, and what will remain inside is just 0 to EF, and then you have 1 minus F and then d dE. Is this clear? Makes sense? I just divided this integral by writing E as this. I divided this integral into these two terms, and of course you should not lose this minus sign. So this minus sign will be carried here. Okay, and then you have the term from here which will come as is. Okay. Now this you can again, so I will not touch this, I will just work on this. So this can be written as minus EF, this piece, this part of the integration, minus EF integral 0 to EF and then d dE, something that looks familiar, and remaining will be minus minus will become plus, and you have 0 to EF F d dE. Right? And you know that this quantity is nothing but little n. This quantity is little n, isn't it? 0 to EF dE dE is little n. 0 to EF dE dE is little n. So this becomes minus n EF. So what, and let me call this integral as I1. Okay, and let me also make one little change. I can take this minus sign inside, in which case this will become EF minus E, right? So it will become EF minus E if I absorb the minus sign inside. So my I1 integral is now this, EF minus E times 1 minus F d dE, minus I have EF times n plus that and plus that. Okay. So then what I have now is I1, then from here I have minus NEF, and then I have this term and that term, plus 0 to EF F d dE plus this term over here, EF to infinity E F d dE. All right. Now the last manipulation, and after that we are done. So what I am going to do now is take this integration, this integral, this piece over here, and write it as follows. So, again once again I am writing this quantity, this guy. I could have done it together with this, but I am doing it in two steps. I am writing this fellow as E minus EF plus EF, as I did before. As I did for I1, I am doing the same for I2. So, you basically have two primary integrations, I1, I2. So, I first dealt with I1 by writing it like this, the E over there, and now I am doing the same over here. Okay, so what will that give me? So, that give me a piece which has E minus EF, and the other piece which has EF. EF is going to come out, and you will be left with F D D E. Okay. So, let us do it. So, if you expand this, it will give you, so I am not touching first, second and third term, plus I am just expanding this integral into two parts. So, you have EF to infinity E minus EF times F d dE plus EF will come out of the integration sign, and you will be left with integral 0 to infinity. Let me use a different color for this part, and you have F d dE, F d dE. So, what have I achieved by doing that? You see, I made a mistake and you didn't point it out. Can you tell me where is the mistake? Here? 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 Where? The third term? Sorry, it should? You can remove your, you can lower your mask.
It should contain EF.
It should contain EF. Yes, it should contain EF. Should it? No. Yes, it should contain an EF. That's true. So, we missed an EF. EF should be multiplied here. Thank you. That's one of the mistakes. Besides this, anything else which is missing? Anything which is missing in this piece? Integral ki, the unit of integral is not correct. It's a EF to infinity. So, it should be EF to infinity. Very good. All of you are very alert. That means you all like maths more than. Okay, I should stop myself from saying that. So, EF to infinity and 0 to EF. Can I combine these two integrations? Integral from this piece, the third term, and the fifth term now, because now it's I have divided the fourth term into 4(1) and 4(2). So, I can combine these two, right? So, I am combining this one, let us call it 1 and 2. They have the same integrand, same limits. So, they can be combined. So, then what I will get then is, I will get I1 minus NEF plus EF, and then since I am combining this, so this is 0 to EF and this is EF to infinity, so it will become 0 to infinity, and what is inside is just F d dE, and I have this integral I2, where I2 is this. This integral has been named I2. Now, who will tell me what is this quantity? 0 to infinity f d dE. 0 to infinity f d dE is little n, right? So, this is number of particles. So, then you have I1 minus NEF plus NEF plus I2. These two gets cancelled out. What will remain then is just I1 plus I2. Is that fine? Now, what is now we are close to the final result. So, I1 is over here and I2 is over here. Do you see any commonality between them? They look fairly common, except that, I mean, let's stare at them very closely. This integration has a limit from 0 to EF, and you have EF minus E sitting here, 1 minus F sitting here, and then you have DDE. On the other hand, in this integration, the limit is from EF all the way up to infinity. You have E minus EF instead of EF minus E. Instead of 1 minus F, you have F over here, and then you have DDE as it was here DDE. Can you give me a physical interpretation of this? You see, they are somehow complementing each other. Here you have 1 minus F, here you have F. Here you have EF minus E, here you have E minus EF. Well, that is not very important observation. The observation is that here you have F and here you have 1 minus F. What is F? Correct. Correct. F is the probability that the energy level at E is occupied with a probability F. So, it is not occupied with a probability 1 minus F, right. So, basically if you look at this integration gives you the energy cost in taking an electron from within the Fermi sphere to the Fermi surface, and this is the energy required to take that electron from the Fermi surface to an empty quantum state outside the Fermi surface. Okay. So, this integral corresponds to this part, if you like, and this integral corresponds to this part, if you like. This integral gives you the energy cost in removing an electron from inside the Fermi sphere and bringing it to the Fermi level, because this is EF minus E. So, your energy cost in bringing up to EF from an eigenstate which is located at energy E less than EF, and this is E minus EF. So, here E is greater than EF. So, this is the energy cost, energy used by the system in putting an electron from the Fermi energy to an eigenstate at energy E, which is outside the Fermi energy, and you are occupying that state with a probability F, and you are vacating that state with a probability 1 minus F. That is the. So, therefore, you can note it down that the interpretation of this term, this integration, which corresponds to this region, this is I1, and this integration corresponds, the second integration corresponds to the energy associated with occupying this region, that is I2. So, I1 is the energy associated with removing, I mean, I don't know if removing is a good word. You can choose a better word for it. An electron unplugging, no, even that is not so good. Think of it, an electron from a quantum state or energy eigenstate, from a quantum state at E, meaning having energy E, which is less than EF. That means the quantum state is inside the Fermi sphere, and bringing that electron onto the Fermi surface, right? It at EF to a, to the quantum state at EF. And similarly, this quantity, I am not writing it, you can write it in your notes, energy associated with then taking this electron from the Fermi energy to its final location, which is some quantum state above the Fermi, outside the Fermi sphere. Now we are ready to calculate the specific heat. We just need to integrate it. So it will be del I del T, del I1 del T, del I2 del T. That's the specific heat. Oh, I removed it. I erased everything in a jiffy. I may probably should have kept the definitions of I1 and I2. So let me leave it to you. So then CV would simply be del U del T and this will be then del I1 by T plus del I2 by T. Okay, and in del I1 you have 1 minus F. So when you will integrate it, when you will take the partial derivative of it, that one term will vanish, will disappear. So you will get only del F del T, because F is the only function which is temperature dependent. Density of states are not temperature dependent, they are static, they are frozen in, right. You fill the states, their filling is temperature dependent, and that is governed by factor F. That is why I said the white line is the white line, that is the density of states. That will, so what will change is how you are occupying these densities, these states. Their occupancy is temperature dependent, right. So this factor is temperature dependent. The temperature dependency come from here. So that is why when you will take the temperature derivative, you will have only del F del T term. So what you will get then from both the integrations, and then you can combine the two integrals, because one integral is from 0 to EF and the other one is from EF to infinity, right, and one is with F and the other one is with 1 minus F. So from both you will get del F del T, from one with positive sign, another with negative sign, and you know in one integration you had E minus EF, in another one you have EF minus E. So you can correct those signs, right. So you will get 0 to infinity E minus EF del F del T and then d dE. That is what you got. Now I can, at this point in time, since I am left with very few terms, I can take the liberty to write this as d of E explicitly. Now here is a catch, a very important point, which is that this quantity over here, so if you look at the form of Ft, if you take the temperature derivative of this, you don't see actually the temperature derivative here. From here it's not easy to deduce because we have plotted it as a function of energy, but you know the form of it. The form of F is this. 1 over exponential E minus EF by KT, KBT plus 1. So, you take the temperature derivative of this quantity and then multiply it with E minus EF, okay, and then you plot it as a function of E. You can do all that, and you can do all that very easily. That will be a homework problem. You would see that this quantity, it actually peaks at EF, and then it falls off very, very fast as you move away from EF on either side of EF. That is the property of this quantity. You should go home and try to verify it. You can use MATLAB or something to plot this function. You know f, the functional form of f. Okay. For EF, you can fix some number. It is a constant, and then you plot it as a function of E. Okay. So you will see that if you plot, because everything you are doing as a function of E, integration and all. So this actually is, this quantity has a significant value. I am not saying has a significant value at EF, around EF, significant only in the vicinity of EF. Therefore, what we are going to do is, from this integration, we are going to take for this, we are going to replace this by dEF, density of states at the Fermi energy. Why? Because on either side the integration is anyway 0, because the integrand is 0. There is no contribution, because this function is decaying so fast. So, this function is basically, it looks like this. It looks like this. In fact, it has a, at E equal to EF, it has a singularity, but otherwise, you know, it is a very sharply peaked function. It goes like this on either side. So, your integrand itself is 0. So, what will you get from this integration? Nothing. Basically integrating around EF. So, you replace density of states by density of states at EF, and if you make that change, and along with that you also, you know, make a substitution. You take E minus EF by KBT. Let us assume this to be x. We are going to change the variable of integration from E to x now. Okay. So, then f, you know, is written over here. So, your f will become 1 over e to the power x plus 1, is not it so? Because you have taken that quantity to be x. And now you can differentiate this, because you need del f del t. So, you can differentiate it with respect to temperature. So, you will get minus 1 by e to the power x plus 1 whole square, and then you differentiate that. So, you will get 1 e to the power x, then del x del t, and since you know x, so you can get del x del t. So, if you do it all, let me just write down the final result. So, you should get del f del t to be, let me keep to be x e to the power x over e to the power x minus 1 whole square into 1 by t. Okay. Or you need this quantity. So, E minus EF will be x times KBT. So, therefore, your this quantity E minus EF times del F del T will become, so for this you write x kBt, and for this you write this quantity. So T will get cancelled out from the denominator. So it has this piece over here. Sorry? Ex plus 1. So you have this piece which will sit here, and then you will have 1 by T, and this T will get cancelled out. So you remain only with x. So therefore, then your CV will be and of course you can write dE in terms of dx. So dE will be 1 by kBt times dx, and you can change the limits of the integration. So you will get something like this: kb square, dEf will come out of the integration sign. Kb square is coming from here because you have this kb and you will have 1 kb in the bracket. Have I missed out something? Yeah, I have. Yeah, this kb, and this should be 1 kb over here also from del F del T. Just check it. So this should be kb square. dE is kBt dx, that's right. So when you will replace dE by kb, so 1 kb will come from there and 1 from here, so it will be kb square. And then dE is coming out as dEf. And then what remains inside is just this. So you have the limit of integration is from minus EF by kBt. Yeah, minus EF by kBt. So when you will switch to new variable, x variable, then this will be the limit of integration, and this will be x square Ex over e to the power x plus 1 whole square dx. All right. This looks nice, except that this integration, the lower limit of the integration is not so good. Otherwise, this is a standard integration, right? But you see, now we are going to use an approximation. We are going to write a condition under which the expression that we are going to obtain will be valid. So for ordinary temperatures, which means even room temperature, for a Fermi gas in a metal, electron gas in a metal, so the temperature kBt EF is much greater than kBt for all practical purposes. I mean, at least near room temperature, you know that this is very easily satisfied, because kBt is of the order of 300 Kelvin, and your EF, you remember yesterday I told you EF for even sodium is 37,000 Kelvin, right? So EF is much greater than kBt for ordinary temperatures, and by ordinary I mean certainly room temperature. Okay, so for ordinary temperatures, what that means is that I can take this as minus infinity as the limit of my integration. Why? Because EF by kBt is a very large quantity, kBt being very small compared to EF for ordinary temperatures. So therefore, this integration will then become minus infinity to infinity x square Ex divided by Ex plus 1, which is a standard integral, and the value of this integral is pi square by 3. Okay, so therefore, what we got for CV of an electron gas, the exact result is pi square by 3 kb square dEf. this completes the derivation. And is there anything else that comes along? And of course, there is a t which I missed here. When you switch the integration, sorry, I did it in a hurry. When you change the integral from e to x, you will get a factor t. This t is here, kbt. So just as he said kb will come, t will also come. So that kb will multiply with this kb and give you kb square. So there is a t here. This t is important. It is for this t that we worked so hard, right? So now you have seen that you have a prefactor gamma, and then you have a t. So this is the coefficient of t. So we have shown through at the end of a lengthy derivation that the electronic specific heat, the specific heat of electron gas increases linearly with temperature for all ordinary temperatures, right? In fact, if you plot Cv versus T, then it's going to look like this. This is a quantity that increases linearly, and then of course it becomes, this quantity will be how much? This is the classical limit, 3/2 n kb. This is the linear regime where Cv is proportional to T, and this regime extends for very high temperatures. You imagine this temperature is close to the Fermi temperature. Unless you reach close to the Fermi temperature, you don't reach the classical limit. So you reach the classical, so this is like Tf, close to Tf, okay. So at ordinary temperatures, the specific heat, even at room temperature, the specific heat is of a metal is linear. That's point number one. If you remember, the lattice specific heat is also quantum, and we had to use quantum theory of solids to explain the lattice specific heat. There also it reaches the classical value, but what is the characteristic temperature there? The characteristic temperature there is the Debye temperature, right? And Debye temperature is of the order of few hundred kelvins, right? For instance, for copper, the Debye temperature is 400 Kelvin. So by 400 Kelvin, you would definitely reach the classical limit. You would have recovered, you would have reached the specific heat of 3 kBt, right? The Dulong-Petit limit. But at 400 K, for the same copper, the electronic specific heat would still be going linearly, and linearly with a very small slope. Now let me comment on the second part of it. How small is the slope? This is the slope of your of the line. This is the slope. How small is this slope? So let's try to see how small or how big is this slope. Just 2 more minutes. So this coefficient is often called gamma in the literature. So this coefficient is pi square, or gamma t is equal to pi square by 3 times kb square def times t, right? Now you remember yesterday, in yesterday's lecture, we derived a very important relation that density of states at the Fermi energy is 3n by 2e. You remember that? 2ef. Yeah? So we can plug that in over here. So then your Cv would be pi square by 3 times kb square times 3n over 2ef times t, right? You can cancel whatever factors you want to cancel, but I will not cancel them. I will rather keep them because I would like to put it in a form which is easily relatable. So you can write this as pi square by 3 times kbt over EF times 3 by 2 NKB. I've just rearranged the term. This split this KB into 2 KBs. This T has come over here, EF is here, this 2 is here, this 3 is here, this 3 is here. Everything is there, but just rewritten it in a slightly different form. This is your CV, and now you are in a position to comment on how small is this CV compared to the classical value, because your classical value is in this bracket. So, it is larger or smaller than the classical value by this factor. So, let us comment on this factor. So, in this factor, the first part, pi square is close to 10, 10 by 3 is close to 3, right. So, the first factor is 3, no big deal. So, this is a 3 factor of 3 sitting here. EF is of the order of 10 to the power 4 Kelvin, if we write in terms of Kelvin, and KBT is of the order of 10 to the power 2 Kelvin at ordinary temperatures. We are just talking about order of magnitudes. So, this is 10 to the power 2, this is 10 to the power 4. Okay, forget about this factor because we are talking about orders of magnitude. So, 10 to the power 2 by 10 to the power 4. So, this is 1 by 100th. So, this whole factor is about 1 by 100th of the classical value, even at room temperature, right. Is this clear to you? For instance, for sodium, the denominator will be 37,000. The numerator at room temperature will be 300, and this factor is 3. So, in the numerator you have 900, in the denominator you have 37,000. So, that is how small the electronic specific heat in sodium is compared to the classical value, even at room temperature. This was my aim. This is what I wanted to show you in this lecture, that CV goes as T and CV even at room temperature. So, the room temperature will be somewhere here. This is your room temperature on this scale. Sorry, this is your room temperature and this is your KBT. Okay, we can stop here. So, for real solids at very, very low temperatures, how will the specific heat vary? Gamma T plus beta T cube, because the lattice specific heat at very low temperatures goes as T cube. When you increase the temperature and you go on increasing the temperature, the lattice term will start increasing more faster than T cube and then eventually saturate at a value 3 kb. But the electronic specific heat will continue to grow linearly with temperature. But this growth rate is so small, this prefactor is so small that you do not really see it unless you go down to very low temperatures. And at very low temperatures, what is going to happen? So, this is your C total. So, C total is CV total, tot is equal to CV electronic plus CV. By the way, this V is at a constant volume, CV lat. Okay, so CV, this is gamma T and this is beta T cube, right. So, in fact, there is a temperature below which your electronic specific heat will be even larger than the lattice specific heat, because it is going as T cube. So, function which is decreasing as T cube will do something like this, right, whereas the linear function will do something like this, right. So, this is your lattice term which is larger at all temperatures, but below a very low temperature you will see that the linear term dominates. Is this clear? This is clear to you, right? Gamma T at some temperature, the function, if you plot gamma T and beta T cube together on the same scale, then beta T cube will be below gamma T line, below a certain temperature, which you can find out from here, by the way, right, by setting it to. This is it. Do you have any questions? Because we have finished it now.